Hey team, today we're going over hypothesis testing with two small samples. And so, have you ever had a friend, maybe they like cats a little more, or you have a friend who like dogs a little more, and they have to compare their vet prices and how much it costs whenever they go to the vet, and maybe the cat's more, maybe the dog's more, maybe they would make a claim that one's more expensive than the other, or maybe they say, actually I pay about the same for my dogs and cats when I go to the vet. Well, let's check out the problem that we have here. So with dogs and cats, a pet association claims that the mean annual costs of routine veterinarian visits for dogs and cats are the same. The results for samples of two types of pets are shown below. At a significant value of 10%, can you reject the Pets Association's claim? And this time, in this case, we'll assume the population variances are not equal. Okay. So under two samples, here we have our sample for the dogs. And so the sample ended up being about $225, sample mean, and the standard deviation of 28. And we had seven visits for our sample with the dogs. And the cats, the sample mean was $203 with a standard deviation of 15, and the number of visits for those was 10. Alright, well, let's go ahead and figure it out. So we need to find a few things. We need to state the null and the alternative hypothesis, find the critical values, identify the rejection region, decide whether we're going to reject or fail to reject this claim, and then interpret the results. The most important part, being able to interpret what we just solved. Alright, let's get to it. So the first one, let's go ahead and state the alternative and the null hypothesis. So the null and the alternative. And then we'll see what they're claiming. So it looks like they said, in our example, that the visits for dogs and cats are the same. That means the population for one of them, the population mean, would be equal to the other population mean. And that's what they're claiming right there. So we can just put a little note, that's what they're claiming. Which means the alternative, and again the null hypothesis always has a property of equality, so the alternative, well, that means they would not be equal to each other. There we go, and that's not what they're claiming they are the same, dogs and cats. So there we go, hey, part A. Part B, let's find the critical values. Okay, well, there are a few key pieces of information we need to think about. And so here we have the property of equality, here's not, and it's an equal test. It's not a greater than, it's not a less than. We're saying these things are equal. Hey, that's good to know right away. I know it's going to be a two-tailed test. Let's see. Other key information. Let's see. They said the variances are not equal. Okay. So when we're looking up the degrees of freedom, and they said the variances are not equal at the very end, this last sentence here, that means we're going to calculate the degrees of freedom by having the first set of samples, or we'll take the other set of numbers in -1. But we're not going to take both of them, we're going to take whichever is smaller. The degrees of freedom. So it looks like the smaller one would be dogs. So the degrees of freedom, n7 minus 1, would be 6. Oop. Wrote it in my head. Alright, we have 6. And the other piece of information, we already have it given to us. The level of significance will be at 10%. Okay, so we need to look at our critical value. So, we're not on the z-score, we're doing small samples, so there's a t-sample, t-distribution. So, our t sub 0, our critical value, will be at, let's see, we'll have to look at the chart. Let's pull it up. So here we have a chart, our t-distribution table, and it looks like this one already has calculated it out for our two-tailed. And so our degrees of freedom was 6, so we go down to this 6. And then, let's see, we're not on a one-tail, we're at a two-tailed. It makes sense, with 5% being a one-tail, 10% for both of those. So it looks like our degrees of freedom is staying with 6, so that gives us a critical value of 1.943. Alright. And let's go ahead and draw a little picture, see what we have going on here. So we have our normal curve. And so here we'd have our 0, t would be in the 0, and you have about 5% over here, and you have another 5% over here, and that makes sense because altogether that'd be 10%. So it looks like over here you'd have the negative 1.943, and over here at this value you'd have the positive 1.943. And so anything outside of here we would be rejecting, Anything outside of here, so the left side, we'd be rejecting. Anything in between, we would fail to reject. So let's go ahead and calculate if where our actual value is, if it lands in this rejection zone, or this rejection zone, or if it lands somewhere in the middle. To do that, we have to find the t-value. And so, here's our t-value. However, here, let me make that a little bigger. However, and so it's very similar to the finding the z-value with two samples. We have the difference in our sample means subtracted by the difference in our population means divided by the difference in our standard deviation. However, variance comes into play here because this denominator can be calculated in two different ways. You can either calculate it with this formula, and so I won't get into where these were derived from, but you can either get it from here, or we could calculate the difference in our standard deviations by this one. And that all depends whether you're assuming the variances are not equal or if they are equal. And so in our problem up here, they said the population variance are not equal, which means we're going to use this method to form and find our t-value. And so we're going to use this to find the difference in our standard deviations. So this will be the formula that we're using right here. So calculating this, let's find the numbers from our original problem. It looks like we had the first mean, the first sample mean we had was $225. And the second mean was $203. And here we're saying the null hypothesis is assuming they're equal, and so the population means would be no difference, which would be 0. So the difference in means would be 0, if we're assuming they're actually the same. And below, in the denominator, we'd have the square root of our first standard deviation, and they gave that to us as $28 squared over the number of 7 visits, plus, let's see, we had $15 for our other standard deviations. Square that and divided by 10 visits. And so again, careful when you type this in or calculate it, follow the order of operations. When you calculate this, you should get about 1.90, somewhere around that realm. And so, where are we at? Well, we're actually really darn close to the rejection zone. We landed about right here. Here's 1.94. We're at 1.90. We were really close. However, to interpret this, well, part D, do we fail to reject? Do we reject? It looks like we are failing to reject the null hypothesis. So part D, fail to reject the null hypothesis. Alright, and this right here, yeah, this was part C, what we just calculated. Part B, this was finding the critical zone. Alright, staying organized. And so finally part E, they're saying, hey, can you interpret the results for us? Well, sure we can. We failed to reject the null hypothesis, and so in order to explain what that means, we have to make a statement. Didn't want to zoom out yet. We'd have to make a statement. And so here's what that statement would look like. And so we'd have to say there is not enough evidence at a 10% level of significance to reject the claim that mean annual costs of routine vet visits for dogs and cats are the same. So we couldn't quite say there's a difference. Yeah, sure, our sample showed there was a difference, but when we did the test, well, there's not enough evidence to reject the claim, so we failed to reject that null hypothesis. And so, there we have it. We have a hypothesis test with 2 samples. Hope this helps.